All right. So one of the cool things about gases and when scientists really started learning about ideal gases and whatnot is that it allowed chemistry to really transition from a qualitative science, which is just kind of, what happens, to a quantitative science, which is like real numbers and that kind of stuff. And a big thing is like, if you get given a sample of something, how the heck do you identify what it is, right? Without any kind of advanced materials. So one method to at least find the molar mass of a compound is this method right here. And again, if you find the molar mass of a compound, you really narrow down the options of what it could be because most compounds have pretty different molar masses from one another. So if you want to find the molar mass of a volatile liquid, and volatile liquid just means basically that's easy to turn into a gas. We'll learn more about it a little bit later on. You can use this one, which is called the Dumas method. I'm not sure if I'm pronouncing that correctly, probably not. We'll do this in lab if we haven't already. Overall, it's relatively simple. You grab some kind of container, you add some amount of liquid, an excess amount of your volatile liquid in there, you heat it, turn it all into a gas. The gas will leave when there's an excess amount of it, but at the end, you'll be left with a certain amount of gas in your volume of your container. And then you let it cool and then you weigh it again. And from that, you can find the molar mass. So there's kind of a simple example, which is what we'll do in lab. You can think about, back in the day, they had more sophisticated instruments, and you could still use these more sophisticated ones nowadays. Anyways, this is the Dumas method of molecular weight determination. So, for example, you could do this with chloroform. That's a very volatile liquid. So find the molar mass of chloroform. If 129 milliliters contains 0.494 grams at 99.6 degrees Celsius and 742.1 millimeters of mercury, right? So you had some amount of chloroform, you put it into container, you heated it up probably in a hot water bath, right, to about 99.6 degrees. It became a gas inside of a 129 milliliter container. And then the atmospheric pressure was 720 or 742.1 millimeters of mercury. And then when you let it cool down, you weighed the liquid that remained, and it was 0.494 grams. So again, this is just a relatively plug and chug type of problem. We have our density is equal to our molar mass times P over RT. In this case, we're asked to solve for molar mass. So we want to reorganize the equation to get molar mass isolated by itself. When you do that, you'll get density times RT over top of P. Now, if we think about density, what did we say density was, right? We've said density is equal to mass over volume. So we can then resubstitute that back into our equation because we're not given a density in our word problem, but we are given a mass and a volume. So then this equation becomes mass times RT over PV. After that, we just do some simple plugging and chugging. We're told that the mass of the chloroform is 0.494 grams, so that'll go into our mass. Our R is obviously 0.08201 liters atmospheres over moles Kelvin. So we'll have to make sure that all of our units work out at the end. Our T is going to be our temperature. We're told 99.6 degrees Celsius. We, of course, have to convert that to Kelvin, so we'll add 273.15. You'll end up with 372.75 Kelvin. So we'll plug that into there. For our pressure, we're told 741 millimeters of mercury. We know that every millimeter of mercury is equal to 1 torr, and that every torr, or that 760 torr, is equal to 1 atmosphere. So what you'll end up with, if you do it correctly, which I hope I did, is 0.976447 atmospheres. Of course, check my work and shoot me an email if that's wrong. And then finally, what we need is the volume. We're given the volume of the container is 129 milliliters. Of course, we need to change that to liters, so we should end up with 0.129 liters. If you think about the units here, the atmospheres cancels out with the atmospheres, the liters cancels out with the liters, the Kelvin cancels out with the Kelvin. This mass right here was in grams. We've got moles there as well. So we have units of grams per mole left, which is perfect because that is the units we need. And in this case, you end up with 120 grams per mole, which is pretty spot on, of course, because this is a worked out example. And the molar mass of chloroform, which has a formula of CHCl3, is about 119 grams per mole. In real life situations, it depends how, well you do the experiment and, how good of equipment you have, right? If you have something kind of fancy down here, you're generally going to get better results than a more rudimentary experiment as shown above.